First, I want to ask, so there are two groups here, right? Can anybody speak up?
Yes.
Okay, two groups. I need two people who can communicate with the two groups, so at least one person with whom I communicate and who can then reach out to the rest. Could you please write me in chat, like who is your starosta in the email, in the chat? Uh, is there anyone here today? Nobody?
We have group emails.
Okay, group emails. Great. Could you please write me into the chat the group emails?
Okay, 1 second.
Okay, great. Thanks a lot. Perfect. Okay, let's start. Um, okay, let me share my screen. All right, let's start the class. So, I guess you know which class you came for. This is machine learning for economists. Let me just make some brief class introduction, some background. So this is, first of all, let me ask you a question. Did anyone see the syllabus for the class?
I looked it up.
Okay, so there is a syllabus on your course management system or something like that, right?
Yes.
Actually, I tried to open it and was not successful right now.
Okay, so let me just drop it here on the chat. You can open it and save maybe. So you can download the syllabus here. Now, while you're downloading the syllabus, let me just characterize the course. That this is going to be a course on economic forecasting with machine learning components. So we will be focusing on time series aspects of machine learning. And naturally, we will be talking about time series a lot. So we will follow this textbook by Elliott and Timmerman, which is called Economic Forecasting. This is the book. You don't have to have it. It's a very, very difficult book. It's like a PhD level book. And my goal here is to try to make it as simple as possible for you, because I believe that this is a very, it's a unique book, and it can be, some parts are indeed very difficult, but many things can be taught at an undergraduate level. So this is my goal, to try to teach you stuff from that book at undergraduate level. So, but I will be relying on way more books and way more material. So let's see how much I can fit into this course. So there is way more beyond this book that I will be relying. So I think you should just carefully listen to the lectures and follow the lectures rather than trying to read all of the books, because it's very difficult. It took me very long time myself to be able to make the slides and like material in accessible way. So you should be able to, you should try to follow what I'm talking about. And of course, the slides, everything will be available, and I will talk about it in a second. This is the preliminary plan of lectures. I will be adjusting here and there as I go, mostly based on how fast I go and if there are any questions and things like that. So basically, I'm not going to go through all the weeks. You can see it. Today we are going to talk about loss functions, and if time allows, we will talk about the parametric forecasting problem. And I don't think we'll have the time to talk about bias variance trade-off, so that would be left for the next week, or perhaps for the practice session that are coming on Saturday. Okay, sorry. Then let me say a couple of words about myself. So I'm an assistant professor at the Graduate School of Public Policy at the University of Tokyo. Assistant professor in Russian means docent. In Russian equivalent of associate professor is just professor. So I'm an economist, and my field is international trade and a bit of international macro. But however, okay, so what that means that I'm an economist specializing in international trade, that means that I don't do actively research in machine learning, which is both good and bad. The bad thing is that I'm not a machine learning scientist. The good thing is that I'm a consumer of machine learning methods, and I take them as a consumer. I go deep into them, try to understand how I can apply to the problems that I face. And why this is good? This is good because I can teach you how to use some of the things rather than going into like implementation details that probably you should study somewhere else. Then a bit of my education. I got my specialist diploma and master's degree in software engineering in 2006 in Novosibirsk State University in Russia. I worked for about 4 years, even more, because there were a couple of non-formal years of working experience, then 4 years of formal working experience as a C++, Java programmer. Then I was always fascinated by economics. I switched to economics. I went to the New Economics School in 2009. And then after that, I decided to go for PhD. So I did my PhD in economics at the Pennsylvania State University, where I specialized in international trade. So my email, I guess you already know, it will be on slides. Now, and the slides will be available where? They will be available on Discord. So we will be using Discord. Let me drop this link. I see I cannot select it. Let me drop it into the chat that right now all of you can join the Discord. Okay, so you shall be able to click that link that I have just posted and sign up for the course. And I will put will be putting there all the lecture materials. The tutorials will all be there. And the assignments will be there. And I encourage you to use Discord for all the communication rather than my email, because my email is swamped with I receive, I don't know, 40 emails a day. And sometimes I can just miss your email. So the best thing to reach me is for this class is to write on Discord. If you ever want to reach me for something outside the class or when the class finishes, then write to my email. But while we during the class, I will be faster in reacting to on Discord. I will be checking it regularly. Okay, let me just go for a second on Discord and see how many of you are. So this is, I see that already some of you sign up. Okay, great. Today at the end of the lecture, I will put the slides for today's lecture there. Now, the next thing that I want to ask you right now is go to this Excel worksheet on Google Docs and write your name there. In English and Russian, doesn't matter. And later, today, tomorrow, by Saturday, when we will have the tutorial, please self-assign yourself to a group. Each one has to be assigned to some group of 2-3 people. The groups will be doing the home assignment, so I will give you a home assignment. Okay, it's view only, thanks. Let me see why it's view only. I was supposed to sure. Anyone can view. Sorry, anyone can edit. Okay, done. Check now. Okay, I see that some of you can edit it. So please write your names and then self-assign yourself to groups. And then, like, by the end of this week, I will freeze this and no editing will be allowed after that. And so whatever group you assigned yourself, that's the group you're going to stick with for the next 8 weeks. Yeah, you can, obviously you can decide the groups later. And then I will send you the emails to your group emails after the class today. To remind you about the links. And I see that you started writing group number. It's not the, sorry, it's not the your group number 191 or 192. Let me write it this days. Assignment group number like this. So I just choose like on the first come first served basis 1, 2, 3, 4, 5, any number that identifies your group. Doesn't matter. Just something that would uniquely identify your group. It can be whatever.
Excuse me, and what is the size of the groups?
Yeah, 2-3 people.
Yeah, okay. Thank you.
So now, as you're doing this, let me just say that there will be tutorials. For the tutorials, this Saturday, I will do the tutorials. And from the next Saturday, it will be Victoria Frolova who will be doing the tutorials. And then I think she would need to do some extra week of tutorials somewhere, and you need to negotiate with her. And I believe the same goes for a lecture, because we missed the first week because I was traveling. And so we need to have an additional lecture sometime, but we will, I guess, get it somewhere in the middle. But I will talk to the administrators. Now, a word about assignments. There will be one home assignment, a group assignment, which will take roughly, I mean, not roughly, but exactly 30% of your grade. And then there will be what I call a final project. And a final project is going to be something where each group will get a unique data set, and that data set would you would need to apply the methods that we learned in this course to this data set. I will break down this final project into several sub-steps so that you don't procrastinate on it too much and don't do it all in the final week. And then I will add all the sub-steps up. All right, that's all for the introduction. Let me know if you have any logistics or any other questions so far. Okay. Then if there are no questions, let's start with lecture 1, which is loss functions. And I will be recording this.
Recording in progress.
Okay. So this part of the lecture will be based on chapter 2 of the textbook. This is just for a reference. Again, you don't need to read it. I encourage you to carefully listen to what I'm talking about during the lectures. So let's first, I said that this course is on forecasting and applying machine learning methods for forecasting. Just let me define roughly what is a forecasting problem. It's very easy, but we need to introduce the notation. We have some outcome y that we want to predict, given some information z, some data z. Y may be a vector, or it could be just a number, a univariate. Z, usually in the time series context, we think about z as all the past history of the data. And we add some time t, and we are computing the forecast. For now, it's not so important for this lecture purpose, it's not, the time series aspect is not so important. Then this data z typically includes past values of y, as well as other possibly useful variables. So as you see, often this zt vector is a vector of y and some information xt. If xt is absent from here, then we are dealing with ARIMA autoregressive moving average or vector autoregressive forecasts. And that's, if you don't know what that means, no problem. I'm going to explain it in 2 lectures, 2 or 3 lectures. But basically, the point here that ZT might contain nothing else but the past history of y. And prediction of y is called a forecast and denoted by fz. So given information z, we predict y. Hopefully this is easy, and this is just to set the notation and set the terminology, what we are talking about. Now, the main object of today's lecture is the loss function. The loss function, it's throughout the course, throughout these lectures, it will be denoted by LFYZ, and it describes in relative terms how costly it's to use the imperfect forecast F, giving the outcome Y, and possibly the observed data Z. Very easy. So what is our loss from using an imperfect forecast? The loss function is the starting point of forecasting. It's a fundamental object, and it's basically how the choice of this object affects everything about your forecast. It affects what would be the best forecasting model, how you estimate parameters of that model, and then how you evaluate the resulting forecast and compare with other models of forecasts. So everything starts with the loss function. intuitively, the loss function should reflect the actual trade-offs between different forecast errors. Here are 3 examples. Example number 1, forecast of future budget deficits by the Ministry of Finance. Imagine you're a government worker, you need to forecast a budget deficit for the next year. Your loss function intuitively probably should be based on the relative cost of over-predicting and under-predicting deficits. Why? Because if you are under-predicting the budget deficit, maybe it's not so bad. Sorry, it's bad. Rather, if you compare it with if you over-predict budget deficit, so you allocate more budget or you prepare to be more in debt for the next year, and then it turns out that you needed less money, which might be a better situation with respect to where you under-predicted the budget deficit, you didn't prepare enough money, and now suddenly you need to borrow money to pay pensions and things like that. Weather forecast, the same idea. When you are predicting like a natural disaster happening, it's probably like I'm in Japan, it's probably to be more conservative and predict that the natural disaster is coming more often than it is actually coming. Because if you fail to predict and the natural disaster is coming, then probably it's a terrible situation. Then the third example, also natural forecasting of hotel room bookings. You can imagine that you're a hotel manager and you're forecasting hotel bookings for, say, the upcoming winter season for the next few months. And maybe you're thinking, what price should you charge for your booking reservations? Should you charge a little bit less or a little bit more? If you charge less, then you probably would have everything booked up, and you would realize that you could have charged a bit more. And so then you can earn potentially more money, but then there is a balancing act. If you charge too much, then not enough bookings are happening, and you might not earn enough money. So you need to take that loss into account, and it can be asymmetric as well. Okay, hopefully that roughly gives you an idea where it matters, and all of these examples are mostly about asymmetries of loss. Now, we're taking a bit like a more helicopter view, in the sense that taking a bit like a step back and thinking about where the loss function should be coming from. So the general principle is that reasonable loss functions should be grounded in economic decision problems. So if we are talking about economics, and we are talking about economics here more throughout the class. So, and I will, in the next few slides, I will explain what that means, that the reasonable loss functions are grounded in economic decision problems. So one obvious comment to that is that loss functions should reflect trade-offs between forecast errors of different signs and magnitudes, and that you saw in the previous slide with the examples, that your loss functions might have different values depending on the sign of the loss. You're like over-predicting or under-predicting, then you can have different loss value. And then also generally, loss function should reflect different magnitude. For example, predicting that you have inflation in your economy in the next year of 10%, or say not 10%, but 30% or 35% is probably the same loss if you underpredicted or overpredicted. But on the other hand, if you're talking about like 1 or 2% inflation, then 1 or 2 makes a big difference. And so what if the inflation happens to be 1 and you predicted 2, then you predicted 2 times higher inflation, which is a huge deviation. So like 1 versus 2 and 30 versus 35, definitely they have different consequences for your decisions after that. So in that sense, both sign and the magnitude matters. So then laying out these trade-offs is straightforward, very straightforward sometimes. And the most straightforward example would be, say, you are an investor who wants to allocate money towards a basket of assets, and you want to maximize your profits, and you're thinking which assets to buy. And for that, you need to forecast their prices for the next period. Then your loss function would naturally be based on the profits that you earn and realized returns. That's easy. But also it can incorporate your risk aversion, meaning that if you're super risk averse, then you would take into account volatility of assets, of asset prices, and then maybe you will allocate less to such assets. And taking into account risk aversion and the profits is very straightforward. It's a standard exercise that investors do. Now, in other contexts, it can be very difficult. Here is an example where it's very difficult. Usually, International Monetary Fund, one of the things that it's doing routinely, it's forecasting inflation, GDP, budget deficits of countries. Like, for example, 2 weeks ago, it released the World Economic Outlook, where the IMF economists provided forecasts for all member countries, like 194 member countries of IMF. They do forecasts for inflation, GDP growth, budget deficits, and things like that. Now, when IMF does this forecast, it's a different question how they come up with these forecasts, but it's a very non-trivial matter, because when they're coming up with a number, they say that some country will be growing like 3% versus instead of expected 4%. That can have bad consequences for that country, that can cause capital flow from that country. Investors can lose, foreign investors can lose confidence in that economy. And so IMF might want to bias its forecast a bit to take into account this problem. But now, when IMF biases that forecast and forecast a bit higher GDP growth than it might think, then the country and investors can take that into account, and they can believe more in that economy, and the economy itself might perform even better. So, and then ideally, when IMF does the forecast, it should do all this, it should take all these considerations in mind. And this is extremely difficult, how you would construct a loss functions that incorporates all of these considerations. Then here's another example where it's difficult to come up with the loss functions. Some loss functions can be justified by game theoretical models. And here is the situation. It's a fact. It's a fact of the world, our world, that many forecasts very often have a systematic bias. You look at forecasts of inflation by central banks, forecasts of asset prices, it's everywhere. You see that forecasters systematically make errors, which is a strange thing. If we believe in economic rational agents that are learning through time, why wouldn't forecasters learn, like after 5 years of forecasting, why wouldn't they learn not to make a systematic error? A systematic error means that they systematically say, you take a certain forecaster and that certain forecaster systematically underpredicts the returns to an asset. So the asset price would be like 1, and this forecaster systematically says that it's 0.8, roughly speaking. Why would forecasters do that? And one explanation can be, one explanation is that forecasters are just stupid. But we as economists don't like such explanations, because if you go with such explanations, you can explain anything. So we in economics, we are trying to deal with homo economicus, rational agent. And at least to some degree, we believe that there is certain degree of irrationality, but still we should try to explain the observed phenomena based on rationality first. And so one of the explanations, and here there is a bunch of citations, there's a whole literature that tries to explain this phenomenon of systematically biased forecasts. And one explanation is that forecasters are just playing a game. And here's one example of a game. If you're a good forecaster, you make small errors, and as information appears, as information reveals, like you're coming closer to a date of your forecast, like a month before the forecast, you predicted an asset price to be 1. Then after 2 weeks, you received more information, and now you predict that it would be 1.1. And then right the day before the forecast, you predict that it would be 1.15. And so good forecasters, usually as time goes by and as you approach closer to the forecast, they usually make smaller adjustments because they're so good and they get it right away. While bad forecasters need to make bigger adjustments as the time approaches. Then the bad forecasters, in order to mask themselves that they are good forecasters, to hide themselves, they still make mistakes because they're still bad forecasters, and they make big mistakes. But in order to show their clients that they're to conceive their clients, they might be making small adjustments to their forecast, even though they're making bad forecasts and they need to make larger adjustments. But in order to signal to their clients that they're good forecasters, they're making small adjustments. And so that would bias their forecasts. And so then when you are analyzing such forecasts, you somehow need to take this into account. That's one thing. And the other thing is that from the point of view of the bad forecasters, they're certainly not minimizing some standard loss function. They're certainly minimizing some kind of strange loss function that takes into account their reputation and this idea of trying to trying to deceive their clients. Okay, hopefully that makes sense. Now, one more comment about the loss functions is that they're naturally related to utility functions in the following sense. Think about your microeconomics and consumer choice theory. Consumer has some utility and minimizes that or maximizes their utility subject to the budget constraint. And depending on the choices that consumer makes, utility can be larger or smaller. And in that sense, loss functions are similar. You have a loss between from you're making a choice, your forecast, and then you are choosing the choice that minimizes your loss from the wrong choice. The difference, of course, here is that usually you don't know the outcome, but you want to minimize the expected loss. Then, in that sense, a loss function can be viewed as a negative over utility function. And there is this paper by Granger and Machina, 2006, that shows that explores this idea. And for example, they show that the utility function that corresponds to the squared error loss, which is this, can be only of this form. You can forget about this term because it doesn't matter for your forecast. Your forecast is here. And you see that every time when you're dealing with the quadratic loss function, you are implicitly implying that there is some economic agent who is evaluating that forecast with this utility, which is, of course, a very restricted class of utilities. You know from microeconomics that utilities have a much, much larger class. And that gives you an idea that quadratic loss function that you might have seen in other courses like econometrics is just a tiny, tiny, like just one loss function in this whole universe of potential loss functions that you should be aware about. Now, this is all nice, what I have just talked about, that the choice of loss function should be based on some underlying economic problem, should take into account all kinds of things. But this is very difficult. And so, unless you're an experienced forecaster, you don't do this. What you do instead, you use off-the-shelf loss functions. But even if you're using off-the-shelf loss functions, which I'm going to talk about in a second, you should be still choosing the one that roughly, approximately reflects your trade-offs that you face. Like, for example, if you're dealing with bookings predictions or inflation forecasting or budget deficit forecasting, we talked about that you need to take into account asymmetries in the errors. And so you should use most naturally, you should try using some loss function that has asymmetric values for plus versus minus errors. Okay, let me pause here and see if you have any questions. Did I go too fast? Are you overwhelmed? Let me know.
I think that it was okay. Perhaps I have a question.
Okay.
More general. Is the concept of loss function somehow applies to our usual estimating of regression models, not in the context of time series, but like we just have some function and we want to estimate its parameters.
Yeah. It does apply. So the loss function, as I said, that even though this class is going to focus on time series mostly, almost everything we're going to talk about, you can apply this to cross-section data. That's point number one. Why I choose to talk about time series? So one remark is that if you open a typical book on machine learning or data science, it usually deals with cross-section. But we economists, for us, more natural is to deal with time series. Of course, we have cross-section data as well, but the point is that time series are appearing more often in practical economic problems. And the second point is that if you know how to work with time series, most likely you would know how to work with cross-section, while the other way doesn't work. Because work with time series is more complicated than work with cross-sections. And so that's why I naturally decided to use cross-section as a baseline, like a point of running example. And if you master this, you can apply everything that I talk about to cross-section. And now that is also true about loss functions. Now, linear regression. Obviously, when you're running a linear regression and you're minimizing, what you're doing, you're minimizing some error. Most likely, what you've seen in econometrics, you were minimizing quadratic loss function. Why you were doing it? Because it has lots of nice properties. And because your point wasn't forecasting. Does it make sense?
Yeah, thank you.
You're welcome.
And I have a question about your last thought about off-the-shelf loss function. You mentioned something about minus and pluses, like we are dealing with them separately. What do you mean?
Yeah, I'm going to, like the next coming section, I'm going to give you some more details about loss function constructions and and now I will go through several examples of loss functions.
Okay.
Okay. Great. Let's go to the next part. Okay, so now let's think about desirable properties of loss functions. We just take a step back and we think, okay, we want to come up with some family of off-the-shelf loss functions that will be universal and you can choose for particular problems without thinking too much about some game theoretic foundation or some decision problem. What should be the properties of this family of the off-the-shelf loss functions? So the first obvious assumption is that the loss function should be minimized at the correct prediction. This is fundamental. So minimization of any loss function with respect to the forecast should be minimized at the true value. Nothing dominates the perfect forecast. Now, here I show the dependence of the loss on data. Very often, we don't, and this is I will give you examples. It's here where the loss function depends on z. But first, let's talk about a simpler case when the loss function doesn't depend on z. So if the loss function doesn't depend on z, so that we have just LFY, and we will be using this as an example for many applications because this is a more ubiquitous case. So we see it more often and use it more often. Then we can just normalize the perfect forecast as the loss from the perfect forecast as 0, like doing so, just subtracting take any loss function and subtract the loss function from the perfect forecast. And then we say that we want if our forecast is to be a unique minimum, then we must have the loss function being strictly positive for all forecasts not equal to y. This is also natural. We either hit uniquely with the perfect forecast, or if we don't hit, we always have some loss. Then here's an example where the loss function might vary with z, with the data that is used to make the additional data used to make the forecast. So then it may not be possible to rescale the loss function this way, because you cannot have zeros for all z's. Otherwise, it's not like you cannot distinguish your loss function values at different situations with where z takes different values. And here's an example where it matters. A policymaker's loss function over inflation forecasts might depend on the unemployment rate. Why? Because if the unemployment rate is low, then it's okay to forecast low inflation and not to react with a tough monetary policy. However, if unemployment, back it up. If unemployment is low and you face the prospect of high inflation, then and if your target is to keep inflation under control, then you could potentially rise interest rates quite high, even though you think that you might be over predicting inflation. But unemployment is low, so rising interest rates too much would certainly impact your unemployment, but it wouldn't hurt the economy probably too much if it's small to start with. However, if unemployment is high and you're rising interest rates too much, then you can drive your economy into a recession. And you can lose your election and things like that, because people will be unhappy. And so you have to be careful when you're doing your forecast and take into account which situation you're in, with low unemployment right now or with high unemployment. And then that would affect how careful you are with over predicting the inflation. So that's where it matters to condition your loss on other data used for forecasting. Okay. Now, more properties of loss functions. So pretty much, I give this example with the loss function that depends on z here. I explain it and I leave it for the time being, because we should master first this situation. And that's what will be doing, because dealing with situations like that, it's like the next level, and we will not be doing much of that. You should just be aware that your loss function might depend on some other data besides the outcome. And we leave it at that. And from now on, we mostly will be working with the situation where your loss function doesn't depend on the outside data. Okay, so the next natural property would be that the loss function should be non-decreasing in your error. So if you make a forecast that is further away from your true value in any of the directions, either you underpredict or you overpredict, then as compared to the outcome that is closer to your true value, the loss should be higher for the situation where you are far away. Very natural. So it should some monotonicity. Then the next property is that if the loss function just depends on the error, which is probably, that's what you've seen most of the time, like a quadratic, that would be an example of a quadratic loss function, where the loss function is just error squared. But it doesn't have to be. And this is an example of a symmetric loss function. Then the reasonable properties of these loss functions can be expanded even further. So loss function of zero error should be zero. It should be non-negative for all E of all errors. Then it should be non-increasing and non-decreasing in the errors, something like that. But okay, yeah, I leave it here. This is just restatement of the properties, like non-decreasing property and the perfect forecast property and the normalization. This is just how these properties look for the loss function that depends only on error. Now, a bunch of other properties of loss functions. So one natural property would be homogeneity, where the loss function scales up or down if you scale up or down the error, the f and relative distance between f and y. So this, you can, like an example of such loss function would be f divided by y. Maybe, yeah, just f divided by y. So where you care about the proportional deviation. And for example, in my work in macroeconomics, I used a lot this loss function. It depends on the context. Sometimes it matters to work not with this loss, but rather with this loss. Then another property that you might want to have or you might not want to have is the symmetry. This is what I talked about, that a natural property would be, in some situations, a natural property would be asymmetry. In other situations, it would be symmetry. And probably, so it's written here, symmetry, the loss from the minus error is the same as the loss from the plus error. And probably in what you've seen in your previous life, in all other courses, probably you've dealt only with symmetric loss functions, but again, this is not the only choice. Then the next property is so-called bowl-shaped. Then that means, let me see if I don't have the picture. That means that the level sets are convex and symmetric about the origin. That would look like this. Why you would want to have this property? So this is the error, this is the loss here. Why would you want to have this property potentially? Potentially this property is nice for numerical optimization. If you are numerically minimizing loss to find the forecast, then numerical solvers are very good at dealing with convex problems. It's not the only choice, but it's a very good choice. It gives fast solutions. Then the next obvious property is differentiability. Again, that helps with numerical calculations. And then yet another property is boundless. You maybe want your loss function to be bounded. Here is an example. Suppose that the two United States inflation forecast results in errors of 100% and 500%. Then probably these are astonishing numbers, and they are unlikely to happen for the economy like the United States. So you might just as well put the same loss into this astonishing numbers and say it's zero. Because, or maybe, I mean, not zero, but just some fixed number. And then there is a technical reason why you would want to put the boundness is because you want to have existing expected loss, which I'm going to talk about in a second. Let me see. Okay, yeah, next slide. And by the way, what time do we finish the lecture? We finish it in 20 minutes, is that right? Yeah, in 20 minutes. Okay, let me see how best to spend the next 20 minutes. I have lots of slides, but I think I would probably want to go right away into, I will skip the expected loss. I will talk about it next time. So yeah, I will skip all this stuff. And let's go through examples of specific loss functions. And that stuff that I skipped here, that means that you can read it through. If you have any questions, you can ask. But basically, that means that that stuff either is not, well, it's important to know, but it might be not important for making your assignments. So the stuff that I will be skipping, it's like for your information, but it's not required to be successful at your home assignments. So I skip this stuff because I thought that I will have way more time. So I put more stuff. And let me give you now specific examples of specific loss functions. So we start with the most widespread example is the quadratic squared error loss or mean squared error. That you've seen that a million times in your econometrics classes. As I said earlier, the utility that corresponds to that squared loss is also squared utility. This is just one example where we can construct the corresponding utility functions, but more generally, usually it's difficult to construct the corresponding utility function. So that loss function is very nice. It's homogeneous, symmetric, ball-shaped, and differentiable everywhere. That's why it's used. It has this property that you should be aware of, is that the forecast error penalty increases very fast, and it's not bounded from above, which means that if you have outliers, they're very costly. And that means that when you're doing your forecast or estimating a model based on that loss function, outliers can drive lots of your results, which might not be a desirable property. Like, for example, you have a cloud of points as your data. Like, this is your outcome Y, this is your data X or Z, and you have a cloud of points, and then there is one outlier, and you're constructing a linear model for the forecasting of Y given X. Then if you don't take this outlier into account, your model would be estimated like this, and then a new x arrives, that would be your forecast. However, if you are including the outlier, you would be maybe something like that. And then your new x arrives, and your forecast will be very different. So you're becoming very sensitive to that outlier. Now, your natural instinct might be to throw away that outlier, which is a bad decision if you know that that outlier is the real data. If you know that there's some big error in this data, then maybe you can throw it away. But if you know that this is the real data, and that's what came out, there's no error here, then you should, but still you are uneasy about the fact that this one big observation drives the whole result. Most likely, all of your next coming results still will be here. And so you want to be closer to that cloud than to that one outlier. And so that's, in these cases, using a quadratic loss might not be a good idea. What is a better alternative is the absolute error loss, which is the next one, which is also symmetric, ball-shaped, differentiable everywhere except 0. And it's known to be more robust to outliers. The loss from the outliers doesn't increase that fast. It increases linearly and with the error. And so you don't put too much weight onto the outlying observations. Both of them are unbounded, but that's more important for us is the unbounded property is important for the calculation of the expected loss. But we can skip that. And for us, for you, the more important thing to keep in mind that the squared loss might be, if you're using the squared loss, you might be putting too much of your weight onto a few distant observations. And so the mean absolute error can be a better choice. Now, the next loss function is the piecewise linear loss. That loss function generalizes the idea of the absolute loss. It makes it asymmetric. It's also called lean loss. So you put different weight on negative errors versus positive errors. And here we go. This is your first example of an asymmetric loss function that you might start using. It's also differentiable everywhere except at 0, homogeneous. It gives mean absolute error as a special case if alpha is 0.5. And then if you have larger alpha, then you put, so this will be larger relative to this in absolute value for the same value of error. Then you would put bigger loss for the positive forecast errors and smaller loss from negative errors. And here are a couple of examples of loss functions. Mean squared error, lean, and asymmetric lean, which is the top picture, bottom picture, and symmetric, which is a mean absolute error. So let's start with symmetric. Here's your error on the horizontal axis and the loss function on the vertical axis. You have mean squared. What you see is that, as I explained, mean squared error assigns quadratic loss, obviously, starts increasing quadratically as you deviate from the true observation, while the lean loss increases linearly. But for the smaller errors, the lean loss gives you like, to be more precise, in this range, lean loss gives a larger error than the mean squared error loss, meaning that mean square error loss is more tolerant towards it values the error from the small small error approximately similarly for all small errors, while lean loss values them in like linearly increasing way. And then for the asymmetric lean loss, you can judge this picture for yourself. Like say alpha is large here on the bottom figure, then your error from the positive, your loss from the positive error is larger than your loss from the negative error, and in reverse for the small alpha. Okay, so that gives you an idea of this large class of loss functions: quadratic, absolute error, linear, piecewise linear. The next often used linear function, loss function is so-called linex loss, or linear exponential loss. So let me see. Yeah, let's start with the figure, how it looks. So the point here is that you can have a small errors. So that kind of smoothens out your piecewise linear loss function. It's asymmetric, and then it has this feature that its values not only asymmetrically positive versus negative errors, but also it for here in this example, for negative errors, it gives you almost the same loss for all the negative errors, while for the positive errors, it just shoots up. What can be a context where you can apply this? This is, I don't know, your booking example or your inflation overshooting. If you are undershooting, if you're underpredicting inflation, it can be really bad if you have high unemployment, say, and then, so suppose we're in a high unemployment situation, and then you are over-predicting inflation. And then that means that you need to react tough to rise interest rates high. And then you would drive your economy into a recession. And then, but if you're wrong, then you're probably the loss is very high. On the other hand, if you're undershooting inflation, maybe it's not so bad. Maybe the economy will like go on for a year without a problem, even though the interest rate is not so high. So for you, all these smaller values of the inflation are roughly the same loss. So that's the situation where you can apply this kind of Linux loss. I talked about the intuition, let me go to the functional form. So this is, let me write it in a different way. So you can write it A2 error minus A2 error minus 1. So that's another way to write it. Then, so it's differentiable everywhere, non-symmetric. This A2 parameter controls the degree in direction of asymmetry. If A2 is positive, then loss is linear for negative forecast errors and is exponential for positive forecast error. That was this example, and reverse example, linear for positive errors, exponential for negative errors when A2 is negative. Oops. And then you can define that this nice property of that Linux loss is that it contains the quadratic loss as a special case. So you can say that this Linux loss is a special case of a more general case than the quadratic loss. So by choosing A1, A2 in a specific way, you can approximate the quadratic loss if you need, but then you can be more general. Then you can be even more general. Here's an example of a piecewise asymmetric loss where you break down the error space into sub spaces or like sub intervals, and then for each interval you assign its own loss function for whatever reason. Like lean loss will be a special case where this loss functions are all linear. A symmetric quadratic loss would be a special case like this. More generally, you can capture the whole set of flexible loss functions by having this kind of loss structure. That kind of piecewise asymmetric loss with this structure can capture a large variety of different loss functions that you are dealing with, and this kind of loss function has been used in the literature. So let's see, I have 5 minutes left that I'm skipping this. Binary loss, we will consider that later. So when we will be dealing with the binary forecast. So we can skip it for now. I will come back to this later. Let's talk a bit about level and forecast dependent loss functions. So assuming that the loss function depends on the forecast error, obviously it can be too restrictive, and I already said this. We have 2 lectures today. Is it? Because I thought that there is only one. I prepared only one lecture. Why
Yes,
do
we have 2 lectures in our timetable.
Wait a second. Is it each week is like that? Or only this week?
No, only this week.
Oh, nobody told me this. We have excellent communication here, I see. Oh, this is so bad because nobody told me this. Can you do 2 lectures next week?
We'll have another lesson there.
Okay, I think what we're gonna do is that I will talk to the admin people to have 2 lectures somewhere down the road. I mean, maybe try to find somewhere else to put another lecture, because I prepared only one lecture for today. Sorry, nobody told me.
If so, well, in my timetable, like 22nd of November, there is a gap between your lecture and our next lesson, so maybe somewhere there. But you better ask the study office.
Yeah, I will ask. Yeah, so you're saying November 21st?
22nd?
22nd, November 22nd. Okay. I will ask. All right. So yeah, just a couple of minutes left for this one. Let me see what I want. What's the message that I want to leave you with? Yeah, that looks like a good place to stop. So as I said, that sometimes you can have the loss function that doesn't depend on error, and one widespread example is the mean absolute percentage error, this one, which I used in my research. Then, so it's unitless, its advantages in why I used it in particular, because I wanted to have an error when I was predicting different outcomes at once. So I have a model that have a bunch of predictions for different things, and I wanted to minimize the error for all of these different things. And all of those different things are in different units. And so in order to convert them to the same units, I was using the mean absolute percentage error. So that's what you can use as well. And then you can, depends on what you want to do with that, you can have errors. I was just using equally weighted, but if you care about one thing versus another, you can have different weights on the loss function. Okay, and yeah, here's just one last example, Federal Reserve's forecast of output growth. It's released only with a 5-year delay, which means that Federal Reserve, the United States Central Bank, they construct internally forecasts of output growth for the next quarter. Each month they construct forecast for the next quarter, and then based on that forecast they make a decision about the interest rates, but they don't publish their forecasts of the output growth. They publish their interest rates policy, but they don't say what's their forecast of the output growth. And then they release their those forecasts with a 5-year delay. So in the year 2022, they will reveal what were their forecasts 5 years ago in 2017. So we just observe the released forecast, but we don't know the forecast methods. We don't know what kind of loss functions the Federal Reserve is using. And so there is this paper by Patton and Timmerman who say that the forecast failed to be optimal. The forecasts don't look like optimal if we restrict the loss to depend only on the forecast error. So in order to rationalize the forecasts that we observe, we should take what rationalizes, what kind of loss function rationalizes is the one that puts more loss on the over predictions of output growth than under predictions, and moreover makes over predictions of output particularly costly during periods of low economic growth. I leave you with that, and the next lecture we are going to talk, so there will be tutorials coming this Saturday. Sorry for this confusion. I was completely unaware. Nobody told me about the 2 lecture things. I will negotiate with the admin people to put this additional lecture, I guess November 22nd. And then the last thing I want to say for this lecture is that I want to circle back and say that sometimes you see forecasting forecasts by professional forecasters like Federal Reserve, Central Bank of Russia, some portfolio investors, International Monetary Fund. And you see that they are making systematic errors in their forecasts. And I want to leave you with the thought that it can be, and most likely the case, that they're making the systematic errors in their forecasts, not because they are irrational agents that cannot correct their errors. Most likely they're making this systematic errors because they have their own loss functions. So I'll leave you with that. Thanks a lot for attending and see you on Saturday. And let me know if you have any questions, and I'm going to post the slides on Discord.
Yes, there is a question. In what programming language will we work? In Python or in R?
Yes, Python. Everything will be in Python.
Okay, thank you.
So on Saturday, we don't have like the offline seminars as it's written in our timetable.
Yeah. Thank you very much for this question. Yes, please come to the online only for this Saturday.
Okay, thank you.
But then from the next Saturday, it would be offline. And please use the same link.
Thank you. Goodbye.
Bye.